My name is Adela, and this is a physics project. Today I'm going to be calculating a lot of components in two clips from the game Just Cause 4. One is going to be surrounding free fall, the other one is going to be surrounding acceleration and time and distance, and maybe a little bit of velocity as well. We're also going to dabble a little bit into free body diagrams, and without further ado, let's get straight into it. This is the funny car. I like to call it that because it's given me a lot of funny problems, some funny issues which we're going to be solving in a little bit. I'm going to drive to the airport where I'm going to take the car for a spin and along a 1 kilometer area, and after that we're going to use that clip to calculate acceleration, distance, and time and see if they match up to what I got. As we're going there, I would like to take this opportunity to talk to you about me. Hello, I'm also Jill, except this time, I'm not physical and way faster. Today, behind the screen of my tablet, I'm going to be showing you the exact same things I was talking about before. Nothing's changed, except due to time. I can't speak. I'm so sorry. Due to time constraints, I'm not going to be talking about free fall and free body diagrams because we don't have time for that right now. Let's get straight into it. So, here's the clip. Now, the distance is 1 kilometer. Here's the proof. That's a nice proof. Now let's get straight back into it. Our velocity initial, which I hope you know what that is 0 kilometers per hour. Because, okay, going to be really quick. So if you saw me doing a burnout at the beginning and the speedometer saying like 79 kilometers per hour, that's incorrect because the car struggles for traction off the line and it would hit, oh god, that's not good. It would start going on stable acceleration at the exact same time that a car from rest would. So there is no difference because of burnouts and stuff. Now, so the velocity initial is 0 kilometers per hour. Velocity final is 360 kilometers per hour as well. Ignore, oops, can I move you? Ignore this for now. Our distance is 1 kilometer, our acceleration is unknown right now, and our time is 14.5 seconds. Acceleration is unimportant right now. So, we have to use similar measurements. How about we convert this into meters per second, because it makes it easier. 360 kilometers per hour to meters per second would be used to, that's some vandalism from the last one I was here. Now, so this is King Henry died unexpectedly drinking chocolate milk. It's a little bit violent, but it's the formula that I learned back in grade school. The letter stands for a measurement in metric. Like K stands for kilo, D stands for something, C stands for centimeters, M stands for milli, C doesn't stand for centimeter, it stands for centi. M stands for milli, U is units. So if I was using grams, U would be grams, and here I'm using meters, so U is meters. Down is times 10, going back up is divided by 10. Not defining right now, so we just go down. Every letter we go down, it's times 10. These two aren't important. I don't know what they mean, so I like to ignore them. 1, 2, 3 times 10 to the third. 360 times 10 to the third is 360,000 meters per hour. That's a lot. Divide by 30. We have to divide that by 3,600, which is the amount of seconds in an hour to convert hours into seconds. That divided by that gives us 100 meters per second. So, this is in fact 100 meters per second. Now that we're back in normal terms, let's look at our formula, which is D is equal to VF plus VO divided by T times time. I don't like VO because it's unimportant and it takes up unnecessary space, so we're going to ignore VO. We plug this in. No, sorry. Now our formula is D is equal to VF divided by 2 times T, because we don't like VO. Plug in. D is equal to 100 divided by 2 times 14.5. 14.5 being our seconds, and 100 being our VF. The distance is equal to 50 times 40.5, because 100 divided by 2 is 50, 3 times 14.5 gives us 729 meters. That's a decent distance. Now, as you can see, our distance originally was 1 kilometer per hour. Convert this into kilometers because decimal places 1, 2, 3 spaces. It's 0.729 kilometers. Is that realistic? I don't think so because it's 1 kilometer. And I mean, they were really close, but I'm gonna have to give this one a non-realistic rating. It saddens me to say this, but very sad, very sad. They were off by 25%, which I mean, they were close, but not close enough. Next up is our acceleration. VL is once again 0. Our velocity final is 360 kilometers, and yes, we're going to ignore this for now. Our time is 14.5 seconds, and our acceleration is unknown. So what do we have to do? You have to convert this into kilometers per second, because I realized I don't like torturing myself, and kilometers in this instance is just easier. Because we're not... Oops. Who's this person? That's not a good person. Now, we have to convert hours into seconds. 360 divided by 3,600. Amount of seconds is an hour. Gives us 0.1 kilometers per second. That does not look good. Our formula in this instance is VF is equal to VO plus AT. In this case, we have to isolate. So, once again, we don't like VO, so we just cross it out. I don't like VO. Goodbye. To isolate this time. Isolate. We have to get acceleration alone, so we divide each side by t. VF divided by t divided by t. We get VF divided by t is equal to acceleration. Here, right over here. Good, very good. We simply it's just a matter of plugging it in. 0.1 divided by 14.5. This is our acceleration. 0.1 divided by 14.5 is 0.007 kilometers per second squared. To convert that back into hours, we just meters now. We're doing meters. Okay, so convert it back into meters times 10 to the third, and we get 7 meters per second squared as our acceleration. As we're using a supercar, it's realistic. Why? Because according to a source that was there, now it's not. Car accelerates at 3 to 4 meters per second. Oh, that's my pen. On 3 to 4 meters per second squared on average. That's just for regular cars, right? It's a supercar, so it's going to accelerate harder. So, I think that 7 meters per second squared for a supercar, when regular cars such as a Honda Civic, Honda Sonata, and Toyota Corolla accelerate at 3 to 4 meters per second squared, I think that's pretty realistic. It's a realistic check from me. Time. Something I'm desperately looking at right now because I need to get this under the quota that I have. I don't know what a quota is. Now, time. Our distance is 1,000 meters. Why? Because kilometers to meters just times it by 10 to the third, which gives us 1,000 meters. Velocity final is, oh god, I'm just hopping around from units to units here. Okay, so I'm gonna use that one. 100 meters per second. Why is it squared? It's not supposed to be squared. It's a regular 100 meters. Our acceleration is 7 meters per second squared, and our time is unknown. So just a double check because, well, double checking is good. Time is unknown. Our formula is d is equal to VOT plus 1/2 AT squared. Once again, we don't like VL, so we just it's gone. It's not coming back. Good. It's gone. And now, d is equal to 1/2 AT squared. All we have to do now is just isolate it. Oh god, what did I do last time? I was recording. This is so sad. There we go. Now, first of all, what we do is times each side by 2, so we can get rid of the 1/2. 2d divided by, no spoilers, but 2d is equal to AT squared. Now we divide each side by a. And we're left with, nope, not yet. A t squared. 2d divided by a is equal to t squared. We square root each side, we'll do this. And then we're left with 2d divided by a squared, to square rooted, gives us t squared. I mean, not t squared, my apology, just t, just regular t. Yep, no spoilers, my apologies. We plug this back in. 2 times 1,000 meters divided by 7 meters per second squared gives us our time. 2 times Whoops, 1 second. Calculator, come on, do it. Okay. So we have 2 times 1,000 divided by 7 is equal to time. I told you that already. Now 2 times 1,000 is 2,000, so it's 2,000 divided by 7 is equal to time. Oh, it's the wrong one. No. And now 2,000 divided by 7 is 2. Whoop, where did it go? 285.7 equal to our time. Square root that. What's the square root? 16.9. We get that right there. 16.9 seconds. Considering our time, what we measured was 14.5 seconds. I say that this is pretty realistic, considering that they're only 2 seconds off. Wow, that's crazy, huh? And you know what's even crazier? I finished 3 minutes earlier than I thought. That's good. That's very good. That's very good. So is this realistic? Now let's see. Oh no, it's not adding another page. Yes. No. Yes. Now. Is this indeed what rating would I give this? Now, what rating would I give this indeed? What rating? That's a tough question. But you see... Oh man, I forgot what the ratings were. 1 second, my friends. 1 second. You know what? Screw this. Good physics in general. Good physics in general. Okay, good, very good. Now why? Because it got... Did it get the... What? I have 3 things here, correct? I have 3 things. With time. Acceleration. And our distance. Did not get to the distance, but it was very close. So I'm gonna leave this undecided. It's gonna be up to you, dear watcher, to decide. Our acceleration is indeed on point, and so is our time. So let's get a good physics in general rating. GPG, right? GPG. I think that's what it's called. Part 2. Final project. I do believe that this gets a... Good, pretty good physics. No, never mind. Pretty good physics. No. This is a tough one. It's a very tough one. Is it good physics in general or pretty good physics? This is a tough one. I can't decide. You know what? Good physics in general it is. No. Wait, I can't decide. No, I had decided, but now I can't. Oh well. Good physics in general it is.